Class, welcome back to Advanced Aircraft Systems. Today we're going to be talking about electrical systems on the CRJ 700. But first, we're going to get into the basics of electricity, how we deal with it on the aircraft, the basic terms, that type of stuff. So I'm going to break this lecture down into two parts, part one and part two. Part one, we'll start out with the basics of electricity, and here we go. So once again, this module covers how the electrical system operates on a CRJ 700. Due to the complexity of the electrical system, don't get too concerned. It's not that complex, but it is a little more complex, a little more like out there in terms of understanding. So the first thing we're going to do is in part one, review the basic terms and concepts so we're all on the same pages. So we're talking about the same stuff. When I say something, you'll understand what I'm talking about. Then the part two is actually going to be covering the AC electrical and DC electrical systems on the CRJ 700. There may be a little intermixing, but this is typically a good electrical system where you understand throughout. Okay, so what are the terms we're going to be talking about? Well, we're going to talk about relays and connectors, buses, circuits, circuit breakers and fuses, open circuits and short circuits, AC current, DC current, TRUs, and what load shedding is. So that's kind of the topics of this part one. You can read through the minutia here if you'd like. I'm going to move on because we discussed this pretty much in detail as we move through the slide. Okay, let's talk about relays and connectors. This is a remote, larger switch that is controlled automatically or manually by a smaller switch located elsewhere. Now, what do we mean by elsewhere? Well, what we generally mean on aircraft, it's in a positional location where the pilots can control it. So in this case, if you're in a jet, it may be on your overhead panel, your forward panel, or the panel that sits between the two pilots. So, center console. So it kind of just depends on where you need to have that switch located. Depends on what system it's related to. That kind of dictates where it's going to be on the flight. In the cases of the CRJ 700 and other electrical diagrams, a relay or connector is depicted as a line that joins two separate small circles with within a circuit. These relays or connectors are strategically located throughout the electrical system to connect or disconnect electrical service to a circuit or a bus. Relays and connectors can be automatically connected by a computer or done manually depending on the electrical system. So it's important to understand that the aircraft that we fly today, the jets that we fly today, use a lot of computers, and this is how we were able to take out not requiring a flight engineer, that third person on the flight deck. So just keep in mind, as an engineer, this is what I used to do on the 7.2, is I controlled what relays were connected where and how and when. Today, you have a computer that makes those decisions for you for the most part. The pilots can still intervene manually if they want to. So let's take a look at how a relay is depicted on most of the diagrams you'll see in this part of the course. Right here is a relay. That shows a relay that has been closed. As you can see, a solid blue line comes down and touches both sides of the circuit where there are two circles. And that's a closed circuit, so that means it's providing power across that circuit. When you have something that looks like this is what we refer to as an open circuit. In other words, this relay, identified by this little guy right here, that relay is not down and touching both sides of the circuit. So therefore, power is not coming, in this case, from generator number one. Power is coming from another source, probably along this line right here, and then powering bus number one through this relay. So where's that power coming from? Well, it could be coming from the opposite side engine, it could be coming from external power, might be coming from the APU. This doesn't show us in this scenario with this schematic. So anyway, that's what a relay is. This relay is controlled by something somewhere else, maybe up here on your overhead panel somewhere. So there might be a switch right here, or it could be over here. It's hard to say where that switch is. On this one, it's an electrical switch. I happen to know the electrical panel right in this area on the overhead. So it's very possibly right in that area. Okay, moving on. Now we're going to talk about buses. A bus is a point from which a source of electrical power is distributed by a circuit to individual electrically operated items or devices. Now, the reality is there can be a couple individual items on one circuit, but generally you think of it as providing electrical power to one item. In this case, this is what a bus would look like right here. In your circuit breaker in your house, in your circuit breaker panel, this is what a bus looks like. So in other words, you have your main power coming in, and then from that point, the main power gets split off into smaller wires and goes to individual components throughout the system. So for example, down here, we have a generator producing power, provides power in this direction. That is when the relay is closed. And then, of course, the bus, which is one of these kind of things here, uh, splits that power off and takes it to the various items throughout the aircraft on its own individual circuits. On this circuit right here might be a circuit breaker, another one down here for this one, have a circuit breaker, another one over here. It would have its own circuit breakers all the way down, and that's how these circuits are protected, is through these circuit breakers. But at any rate, remember that a bus is a point from which a source of electrical power is distributed. So a circuit is a route of electrical current through a wire to a point where that electrical current is used to provide power to the electrically operated items or devices. So in this case, we're talking about this is our source of electrical power, and this it looks like it's just a battery. This could be a generator, or it could be an alternator, or a battery, whatever can produce current to send down the wire in this direction, and it goes until it gets to the switch. If the switch is open or not closed, then the source of power stops at that point, does not travel on. When you close the switch, then the power can continue to travel on down the circuit to the item that it's going to power up. And in this case, it's a light bulb. This circuit right through here is the return, or commonly referred to as ground. Without the ground, the electricity cannot complete its circular requirements throughout the system. This ground can either be a wire or it can be bonded straight to, for example, the aluminum structure of the aircraft at the place of where the item being powered is operating, and then it can pick up another ground closer to where the battery is. So it can actually, the ground can be the aircraft itself, as long as it is able to conduct electricity. While multiple devices can be powered by a single circuit, regardless, circuits are protected from being overloaded by a fuse or a circuit breaker. So somewhere in here, we would have a circuit breaker, or it might be over here. Generally, the circuit breaker would come Hard to say. It could be before the switch. Sometimes it's after the switch, depending on the choice. I typically like to see them before the switch. So if we have a short or something happen in the switch, we're going to be protected uh, throughout the entire circuit. This doesn't matter as long as we're on the positive side, circuit breaker should work. So now we're going to talk about circuit breakers or fuses. This is a device that creates an open circuit when that circuit breaker or fuse detects excessive current or overheated conditions in a circuit. Now, this is going to be my little lecture box here, uh, where I try to explain to you what you do and don't do with a circuit breaker. So, a circuit breaker is a fuse. A circuit breaker or a fuse is a safety switch that automatically disconnects the electrical service to an item or items that are being powered because of an excessive current being used or overheating occurs on that circuit. Think fire. So if you have a circuit breaker that pops, you think you want to push that back in. Some outfits will say, "Oh, you get to push it back in once," and then if it doesn't stay in, you have to leave it out. Personally, in the airline business, we don't reset circuit breakers. If they pop, we leave them out because there's a reason it popped. So there's probably a short or an overload on that circuit. But there's a reason. There's a reason these things are developed the way they are. Uh, so that if it pops, we're not going to create a fire on the aircraft. Last thing I want to do is be in flight and induce a fire that I didn't have to induce at all. So if a circuit breaker pops, we're going to leave it out. So think of it as being fire protection on the aircraft. So the rule is, as such, do not reset a trip circuit breaker unless the use of that item being powered is necessary for the successful outcome of a flight. So I don't care where you're at. If you don't need to reset that circuit breaker for the successful outcome of the flight, don't reset it. Go without that item. It's fine. Nothing's going to happen. So let's give you an example. You're flying cross country in the middle of the day, and you notice that the circuit breaker on your nav lights has just popped, and now the nav lights are no longer powered. So, question is, are you going to reset that circuit breaker while you're flying along? Absolutely not. There's no reason to reset a circuit breaker for nav lights during the day. Nav lights are not going to make your flight safer during the daytime. A lot of pilots won't even turn them on. They'll leave them off because they want to save the bulbs from burning out. So if it's me, I'm going to leave that circuit breaker out, and I don't care. I can't see the nav lights on another airplane in the middle of the day if I'm 20 feet away from it. Just can't see it. It's difficult to do. Some people say, "Oh no, you can see those nav lights. That's good for being seen." No, it's really not. So in this case, no way am I going to reset that circuit breaker. However, let's say I'm flying at night and the same circuit breaker pops, and I notice that the nav lights go out. Now the question is, am I going to reset those nav lights? Because you can see nav lights pretty readily from quite a distance away. It's going to tell you is the aircraft coming at you or going away from you. Well, here's my thought on it. This is just a thought. Everybody's thoughts might be different. But if I have a circuit breaker that pops out at night on the nav lights, I'm not going to reset that circuit breaker. These nav lights are there to give yourself, give the other guy identification as to which direction you're running, going. It's not going to necessarily uh, help you get the aircraft back to the ground safely. What's going to be a problem is if you push that circuit breaker back in and you happen to start a fire doing it, that's going to be more dangerous than running without nav lights if there's a problem on that circuit for the nav lights. So personally, I'm going to keep the nav lights off. What I'm going to do instead is I'm probably going to turn a landing light on. I'm going to make sure my rotating beacon is operating and or my strobe lights are off. So I have other sources I can use to be seen at night I don't necessarily need to have those nav lights on if they inadvertently went out. Now, we know that the FAR say you have to have them on, but not at the expense of starting a fire. So that's my thought on that. I will do what I think is safest at that point in time. I'm probably going to leave that circuit breaker out. Let's take another scenario. You're in your Cessna 172, you got this wonderful G1000 navigation system, and you filed IFR, and you're now in IMC conditions, instrument meteorological conditions, at night. And all of a sudden, you look down and you notice that the circuit breaker on the G1000 has popped out. Now, what are you going to do? Well, you're in instrument conditions, right? You need this stuff. Well, not right away. You should have about maybe 60 minutes of reserve power on a remote battery for the G1000, something like that. So let's say I had an hour and 15 minutes to my destination airport. Uh, Now I know I'm probably going to run out of reserve battery for my G1000 before I get to my destination. And let's say it's IMC at my destination. So what's my best course of action here? Do I want to push that circuit breaker back in? Not if I don't have to. I might just go on reserve power, notify ATC I've got an issue here, an electrical issue. I'm going to need to divert to a closer airport, and hopefully I can get all the way back to the ground without ever having to turn that, uh, push that breaker back in. On the other hand, if for some reason there is no airport around that's safe enough to land at because the weather's below minimums for those approaches, then I have to go to my destination. So in that case, I'm going to leave that circuit breaker out for as long as I can possibly leave it out. If I can get within maybe 5 or 10 minutes of the final approach fix for the airport at my destination, then I'm going to wait, and then maybe I'll push that circuit breaker in at the last moment so I can shoot the approach. That's about the only time I'm going to want to have to actually use it. But if I can get that far down the road, I'm going to hold off. And then if I do start a fire, at least I'm close enough to get to the ground before maybe the fire can get out of control. So that's my thought on using circuit breakers. At any rate, in the airlines, we don't reset circuit breakers, and we don't even want to take one attempt at it. I'll tell you what I'm going to do. If I'm on the ground, I've got a circuit breaker out, I'm going to call maintenance and tell that mechanic to come out here and push that circuit breaker back in. I'm going to leave the cockpit because I don't want to be responsible for burning down a multi-million-dollar aircraft. So that's how we do it in the airlines. We call somebody out who's probably a lot more responsible than us pilots, right? So that's my little soapbox for today, and let's move on. Open circuit is a condition in a circuit that prevents the current from flowing to an electrically operated item. An example of an open circuit occurs when a circuit breaker is tripped, or a section of wire is broken, or an inline switch is positioned to the off position. So that's basically what this says right down here. We can see right here that this is an open circuit. We can see that our power is coming from this side, but it's open on the ground side, so it's not being grounded. Therefore, that's an open circuit. No power is able to operate our electrical device. Short circuit's a little different. A short circuit is a condition in a circuit when a positively charged wire crosses any other wire or structure that is connected to ground. The result is a tripped circuit breaker. The tripped circuit breaker trips because it senses an excessive electrical resistance and or overheating of that circuit. So in this case, we're looking right down here at where a positive wire has crossed over a ground wire or a structure of the aircraft that's grounded, and it creates a spark right in this area. That spark is additional heat or becomes resistance. At that point in time, the circuit breaker would pop, and that protects us, basically shuts off the electrical current, and therefore we can no longer, it'll no longer be a problem with us starting a fire. So hopefully the circuit breaker is behind this, not in front of it, because if this were a circuit breaker, for example, uh, I take that back. The power is coming from this direction, so if that's the circuit breaker, it would protect us at this location right here. However, if that short circuit occurred back here, there is no circuit breaker between the break in the wire and the source of electrical, so that would not be a good thing. We would have no protection at that point. But beyond the circuit breaker, we do have protection. Okay, AC current refers to an electrical current that switches directions many times at regular intervals. That's important. So we generally want to have generators producing AC current for us. Current produced by a commercial jet airliner operates at 115 volts at 400 cycles. Now that's going to be an important set of numbers you're going to need to remember from here on out in your career. In the airline industry, 115 volts, 400 cycles is pretty standard. For a generator to produce AC power at a constant frequency that will provide usable electrical power, the generator must rotate at a constant RPM. Now, how do we do that? Because we've got a generator hooked to our jet engine, okay? And that jet engine is variable in power and RPM. So if we change the power, we're changing the RPM. So we have to have a method by which that generator can maintain constant RPMs. We do that through the use of a CSD, constant speed drive. Generators are powered by jet engines use a constant speed drive to maintain constant generator RPM, even though the jet engines are variable in RPM. The combined generator and the CSD are called an integrated drive generator, IDG. So you'll hear a lot of pilots talk about, well, we got the IDGs operating properly. What they're really referring to is a combined unit of a generator and a constant speed drive. That's the way we refer to them nowadays on jets. I remember that earlier jets that we actually had a disconnect that we didn't actually had a constant speed drive, but it was called something different, and we could manually disconnect it from the generator. In this case, a CSD and a generator are co-located, co-combined, and we call it an IDG, integrated drive generator. An APU, on the other hand, operates at a constant speed and is not variable. Now, you would have remembered this from an earlier lecture. APUs operate at basically 100% RPMs, meaning that their RPMs are constant when they're operating full speed. So if they're operating at constant RPMs, we don't need a CSD between the generator and the APU itself. We just take it right off the gearbox and power it that way. And we make sure that the generator is synced with the RPMs of the APU to provide 115 volts at 400 cycles. So generators don't need a generators on the APU don't need a CSD. Generators on our jet engine do need a CSD. And in summary, we call that an IDG. Those are located on the jet engines themselves. DC current. This refers to an electrical current that flows in one direction only. Batteries produce such a current. Lead acid batteries used on most small light aircraft are a lead acid battery is what's used on most small aircraft. Some of them are going to nickel cadmium. That's fine. It's a good battery. But generally speaking, light aircraft have generally used normal lead acid batteries, either 12 or 24 volts. Then we have another type of battery, as we just talked about, nickel cadmium. We call them those NiCads for short, most common on commercial aircraft. On the CRJ 700, we have two batteries that are used for aircraft operation. Each battery produces a nominal of 24 volts. One battery on the CRJ is used for starting the APU, and the other battery is used as emergency backup for the DC electrical system. So you can always think of a battery when it's not operating or functioning as being an electrical emergency source for the DC side of the electrical system on a jet airline. Okay. Nickel cadmium NiCad batteries used in commercial aircraft. Well, why are we using NiCad batteries on commercial aircraft? Well, there's three big advantages. Output voltage is constant until nearly fully discharged. We'll take a look at that here in a second. It allows for a high current charging rate, so we can charge it rather rapidly. High current output for starting gas turbine engines. Think about the APU. So we get a lot of power and it stays with us until we get something started. The big disadvantage is what we call a thermal runaway. This is not a good thing on an aircraft. Well, let's take a look at NiCad versus a lead acid. So in the blue line right here, you'll see that that is a lead acid battery. And its output diminishes right as soon as you start using it. The output diminishes and tapers off. Its output continues to diminish throughout its use. On a NiCad battery, it diminishes slightly when it first starts to use, but then its output remains constant until very near the end, within about 10% of its total capacity. Then it will start to drop off, and it drops off rapidly. So it's a much more consistent level of electrical power for us, and the aircraft will run better that way. Just kind of a better battery for that. This is the disadvantage, a NiCad thermal runaway. As you can see, it would not be a good day. Here's a battery that probably came off, who knows, a 737 possibly. And you can see that it had an internal thermal runaway and it melted it. This is what it should look like. You can still see the circuit board. And this one right here, there's the circuitry for it right there. So somehow this battery did not run away, but this one could have caught the airplane on fire. So how's that happen? Well, a high temperature, the battery gets hot, then you have an internal breakdown inside the battery. Then we get an internal short circuit, and then we get a lot of high current flow. And along with all that comes a thermal runaway. Very difficult to shut that thing down. All we can do is disconnect it from all of our rest of our electrical usage. So not a good day if we get a thermal runaway. Not too common. They're getting better at building these kind of batteries. Let's talk a bit about TRUs. This is called a transformer rectifier unit. They are used in an electrical aircraft system to convert AC to DC current, alternating current to direct current. So in this drawing here, blue all up here is AC current. Now this shows you a typical electrical system on the CRJ 700. So blue up here is AC current. Then we have DC current down in this area, okay, in the red. So just keep in mind, most of these commercial aircraft, the primary source for electrical power comes from either generators or an external power source of some sort. And that's only when it's on the ground as far as the external power goes. Otherwise, you have a number one generator, you got a number two generator, an APU generator in flight, and then we can use external power on the ground. But we do not try to power the aircraft with DC power. We have to convert AC power instead to provide power to the DC side of the electrical system. How do we do that? We use TRUs, transformer rectifiers. Just so happens on the CRJ 700, we have 4 of these transformer rectifiers. Let's get rid of some of the lines here, make it a little more clear for you. So here's a transformer rectifier. Here's one, and here's one. Now, if you notice, this aircraft is obviously on the ground because it's getting AC power from an external power card, or it was plugged into the jetway. The relay closes here. Right there, that relay is closed. The other relays over here from the generators are open. And so power to the AC side or the AC bus tie is through the external power card. And a relay closes here and it closes here. And that power powers up the AC bus number 1 and AC bus number 2. From that point, we have the AC bus number 2 coming down and powering up the TR2, transformer rectifier number 2, and AC bus number 1 powers up TR unit number 1. Then we have these essentials that are powered by the AC essential bus, which gets its power from the AC bus number 1 in this scenario, and it comes down here and powers up essential bus or essential TR. And then AC bus number 2 comes down and powers up essential bus TR2. So at that point, the TRs convert AC power to DC power, and then the DC power being in red powers up the DC buses. Of course, what's a bus? That's a place where we split the power off, takes it out to individual circuits throughout the aircraft. DC power batteries are used to power DC buses when normal ship's power is unavailable. Well, what do we mean by that statement? When normal ship power is not available. That means, let's say we're flying along and we're not on external power. We have to be on generator power 1 and generator power number 2, powering the aircraft. Let's say we had a fault in this generator, it goes away, and we end up with a fault, and or we lose an engine, and of course that engine powers this generator. We lose that generator also. If the APU is not already running, we have lost all sources of AC electrical power. At that point in time, we would use power coming from this battery right here. It would power this bus, and of course the circuitry would close and allow us to back power our buses in this fashion and help provide us with some degree of electrical power so that we can continue to control the aircraft. Okay, so very seldom do we actually use DC batteries to fly the aircraft. We always power the DC side of the aircraft electrical system with AC electrical when AC electrical is available. One more term we need to talk about, and this is called load shedding. At times when, well, let's see. Get my slide here to do what I wanted to do. Here we go. Okay, so in short, what load shedding is when we do not have enough power being provided to actually operate the items on a circuit. So we don't want to overload a circuit. So what we do is we disconnect those items that are unessential to the continuation of safe flight. Now, I don't drink coffee, so that's good for me because one of the first things these aircraft, commercial aircraft do is when, for example, if you lose an engine or lose a generator on that engine, if one of the generators happens to drop offline, cannot produce power, a lot of times the operating generator doesn't have enough push to power up all of the items that are on the aircraft. So we would shed some loads. So the first load we're going to shed in most cases is the galley. The galley is a luxury item that makes coffee, cooks food if we were serving food on these aircraft anymore. So if we don't need it, we would discontinue the use of it. Very much the same as if you ended up losing your alternator and all you had left was your battery on your Cessna 172, you would shut down unnecessary electrical equipment so you didn't draw on that battery. We kind of do the same thing by getting rid of unnecessary electrical items, galley being the first thing we would take offline. Doesn't matter to me. I don't drink coffee anyway. So that's the first thing I'm going to disconnect. If I can, I'm going to try to get it back. If I have the opportunity, I might start the APU, which is another generator. Now, in flight, I can use electrical power quite a ways, pretty high in altitude, unlike pneumatic power. Electrical power, I think, on this aircraft goes all the way up to the service ceiling of the aircraft. So I'd start that APU, and then I could go ahead and turn that galley power back on so the flight attendant could continue to serve those passengers their coffee, or at least the other pilot who drinks coffee. All right, that's it. That's what load shedding is. That's all I've got to say about part one of the electrical system. We'll continue on with part two. We'll cover AC and DC electrical systems on the CRJ 700. Stay tuned. We'll be right back with you.